We'll continue our discussion on policy gradient methods. The main idea today, so we talked about the derivation of the policy gradient in TRPO algorithm. I'm going to talk about PPO algorithm for a bit, very small snippet, and then I'll talk about a new algorithm that came out in 2020, which is talking about how to implement the policy gradient method using unbiased estimates of the gradient. Okay, so it's one of the first algorithms that talks about unbiased estimate of the gradients, and that's the main purpose of today's lecture. Okay, so uh, so I'm going to introduce the same set of notations I did in the previous class because I want to make sure that we are all uh, I have all the expressions on the board. So my v mu is summation, well, sigma mu r mu. My q mu is r plus alpha p v mu. Well, I'll have to write it probably as j p I j u v mu I, v mu j. So this is at I comma u, r is at I comma u. And then I have sigma mu equals to summation alpha raised to t, p mu raised to t. T goes from 0 to infinity, which is the same as I minus alpha p mu inverse. And what else? Advantage function a mu equals to k mu minus b mu. And then the policy advantage function L mu mu prime is given by sigma mu sigma mu times mu prime times a mu. I don't know if I should write it fully. Anyways, we'll get to it. Okay, let me write the policy advantage function in the full format. So L mu prime equals to summation sigma pi I prime given I, sigma mu, sorry. Given I, mu prime, u prime given I prime, and then a mu I prime u prime. This summation is over I prime and u prime. And this is a function of I, the initial state I. So maybe I should write it as a function of I. This is the policy advantage function. Okay. So these are the notations we introduced in the previous class. So I'm just writing up those notations again. One thing that I wanted to make sure you understand, instead of this a mu, you can also replace this by q mu. It's not going to change the expression for L mu. So you can use q mu or you can use a mu. A mu is better because a mu generally is smaller in value. Q mu is much larger in value because Q is cumulative reward and value, whereas in advantage function, you are subtracting the value function from Q mu, so this particular term is supposed to be smaller in magnitude in comparison to Q mu. So imagine if U mu is 1 million, Q mu is roughly 1 million, but the advantage function is going to be close to 0. So your algorithms becomes numerically stable if you're using the advantage function here instead of the Q function here. But if you expand the expression, you will realize that whether you use A mu or Q mu, you get the same expression. So it doesn't matter. Okay, so remember that we are always updating the policy as mu k plus 1 equals to mu k plus beta k mu bar k minus mu k. And remember that the space of policies is a convex set in a high dimensional space. So the only question is, how do you compute mu bar k? So in the policy gradient method, mu bar k equals to argmax of mu prime rho transpose L mu prime. That's the policy gradient method. In the TRPO method, mu prime k equals to argmax mu prime rho transpose L mu prime, such that KL divergence of mu prime, I should say mu k here, less than equal to epsilon. So these are the two algorithms we talked about in the previous class. In PPO algorithm, your mu bar k equals to argmax of mu prime rho transpose minus beta k dkl mu k mu prime. Now this beta k gets updated according to some fashion. So let me write down how the beta k gets updated. To beta k if dkl mu k mu bar k is greater than beta k plus 1. Some target into 1.5 and beta k over 2 if this is less than equal to target over 2. No, target over 1.5. Mu k. I should have mu k here. Okay, so that's the differences between different algorithms. And then there is another one which is soft actor critic. It's somewhat different algorithm. So in soft actor critic, this is from 2017 if I'm not mistaken. PPO is also from 2017. This one is from 2015. This one is from 1992. So these are from different eras. PPO 2017. This is 2015. This is 1992. And this is 2017. And here I'm trying to maximize J of mu equals to summation t equals 0 to infinity r of alpha raised to t r of ut plus alpha is already used. I need another notation. Let me use lambda entropy of mu it. So this is the entropy. So I don't know how many of you have seen this term entropy before, but if you have not, you can go back and look up Wikipedia for the expression for entropy. But here, so instead of solving the original problem, which is trying to minimize this particular term, I'm now going to add to the reward function lambda times the entropy of the policy evaluated at every action. So remember, policy is a distribution over the action set. So I'm going to penalize I'm going to encourage high entropy policies, and I'm going to discourage low entropy policies. What is a low entropy policy? It's a deterministic policy. So I don't want to have a deterministic policy. It has low entropy. I want to have more of a stochastic policy. But then how do you know what's the best stochastic policy? You uniformly pick any action. That's the best stochastic policy that maximizes the entropy. So entropy is maximized at uniform distribution. So at every state, you pick all actions with equal probability. That's going to maximize the entropy. But I don't even want that because I need to optimize the reward. So this lambda kind of balances the trade-off between whether you want to use high entropy policy or whether you want to optimize the reward. So for small values of lambda, you get the optimal policy. I mean, if lambda equals to 0, you're essentially optimizing this. And if lambda is very high, then you're not optimizing the reward, you're optimizing the entropy, which means that your actions are going to be uniformly distributed for every state. By the way, my personal opinion is that many of these papers are very poorly written. So I get confused a lot when I'm reading the paper. I'm assuming that you don't get confused a lot, but if you get confused a lot, it's completely fine. It's normal. These are written by very influential people, so don't get me wrong. They are very solid researchers, but it's just that the way they have written the paper is mathematically challenging for me. For people who read mathematical papers, for me, it's very difficult to read those kind of papers because there's a lot of intuition in those papers that are unsaid. So anyways, this is the problem that they are trying to optimize in the soft actor critic paper. And the algorithm there is, let me see what the algorithm is. So here, mu bar k plus 1, mu bar k equals to argmax mu prime dkl mu prime exponential q mu over z mu. So z mu is the normalizing factor. Okay, so exponential of q mu, so q function corresponding to this this reward function. So remember, the reward function here is the reward, the original reward, plus lambda times entropy. So you figure out the q function for this particular reward, and then you normalize it so that this whole thing, the exponential of q mu, becomes a probability distribution. So essentially this, you can think of this as q mu k, z mu k. So let me think of this particular thing as a policy C u given I exponential q mu k IU over summation exponential Q mu K IU sum over all IU. That gives you this particular policy CK. If you remember, this kind of thing was also used in SARSA. This sort of policy was also used in SARSA. And so there is some connection between what you did in SARSA versus what you're doing in soft actor critic. So these are different types of policy gradient methods. Okay, so each has its own philosophy of what they are trying to do. So if you recall, this one is vanilla steepest descent method. This one is steepest descent method, but with some sort of trust region. The trust region was constructed using the second order term in the policy perturbation result that we discussed in the previous class. Then PPO says, look, why do you want to add this constraint? By the way, the first author of PPO was the same as, like you mentioned, he's also the first author of TRPO. So I went back and checked and it turned out to be correct. The rest of the authors are different, but the first authors are the same. So the PPO author was the same as TRPO first author. And at this time, he was already at OpenAI. So this was being done at OpenAI, this particular work. And so they said, why do you want to put this as a constraint? Let's just add a hyperparameter beta k with the KL divergence. And then I'm going to update beta k according to some target for the KL divergence. Okay, so if the KL divergence is very high, I'm going to increase the value of beta k. If the KL divergence is very low, then I'm going to reduce beta k by half. And that's their update term in PPO. There's some more stuff in PPO, but we'll get to it in the next class when I talk about importance sampling. And then the PPO was then further improved by soft actor critic by saying that, look, I want to explore in the beginning, and then I want to stop exploring towards the end. So how do you explore in the beginning? Well, you add an entropy constraint, not a constraint, but you add an entropy regularization to the reward function, and then you optimize based on this entropy regularization. Okay, is that does that make sense? The main conclusion of soft actor critics, of course, in my group we have mostly used PPO algorithm, and that too very like we have not. I'm more of a theory researcher. I don't do experiments, so we just did experiments on PPO. But the soft actor critic papers claim is that this algorithm turns out to be better than PPO for continuous state, continuous action MDPs. And we haven't talked about continuous state, continuous action. So one of my main challenge when reading these papers is that they start with discrete state, discrete action, and then in the simulation section, everything becomes continuous state, continuous action, and I'm not able to reconcile how they went from discrete to continuous. But anyways, it can be done. So anyways, this was designed for discrete state action stuff, and then it moved to continuous. So in the simulation section of this paper, they've said that soft actor critic does better on continuous state, continuous action problems like robotics in comparison to PPO. Okay, so that's roughly what the idea is. Any questions so far? Okay. So now the goal for me is to, so right now what I want to do is talk about, so remember that in order to compute each of these quantities, you need to know the probability function, you need to know the reward function and everything, right? So all of this stuff is something that you already know, only then you can evaluate this. And once you evaluate this, you know the initial distribution, you can now solve this problem. Now the question is, in reality, we only have samples, right? That's what reinforcement learning is about. We have samples, and from samples, we want to be able to estimate this, right? So the question is, how do I estimate this? How do I come up with an unbiased estimate of this particular quantity? Okay. Now there is, of course, naive estimators that you can use, and let's talk about the naive estimators. So this is so what's the problem? I cannot compute this exactly because I don't know any of these things, but I have a simulator, and in the simulator, I can simulate the state, action, reward, and the next state. So if I have that simulator, how do I come up with an unbiased estimator for this particular term? Okay. So remember, this term is, let's say, rho transpose this. I'm going to write it as rho I and sum over all I. Okay. So now while I'm erasing the board, I want you to think about, if you only have a simulator, how are you going to estimate this particular function? How are you going to estimate this function? So I want you to think about it while I erase the board. Any questions so far? Okay. Okay, naive estimator. Anyone wants to try? How would you estimate rho transpose this thing? Let me write it in the full format. So remember, I have to replace the sigma mu by alpha raised to t p mu raised to t. So let me do I rho I summation t greater than equal to 0 p of st equals to it equals to I prime. Let me write it as p mu given I0 equals to I. No, I need alpha raised to t also. And then I need I prime u prime. I have this, and then I have mu prime u prime given I prime. So how would you solve this problem? How about I collect all these terms, summation over I, summation over I prime u prime, summation over t greater than equal to 0, rho I alpha raised to t, I prime given I, mu prime a mu. How would you do the estimate for this? So remember, what we have here is a function of, so I start with the initial state I with probability rho I roll out this under the policy mu. I do the simulation until I prime u prime for t time steps, and then I collect all of these functions, multiply them together, and then I sum it up, right? So the naive estimator would say, let's pick an I0 from this distribution, run it for t time steps, then you get I prime, evaluate a mu at I prime u prime, multiply it by mu prime of whatever, multiply it by alpha raised to t and sum it up. You do these simulations multiple times and you can get a good estimate of this particular value, right? And that's true, you can get a good estimate, but it's not going to be an unbiased estimate, okay? Because at some point of time, remember you have an infinite sum here, t goes from 0 all the way to infinity. You cannot really run it for infinite number of time steps. As a result of which, what you are going to get is a biased estimate of this particular thing, because you will stop at some point of time. You will pick a big enough t, and then after that you will say, let's not estimate beyond t equals to 100 or 1000 or 1 million, whatever your favorite number is. And that becomes a problem. The other thing that I wanted to make a change here is now my mu is going to be a function of theta. So I'm going to look for policies within a parameterized class of policies, such as a neural network. So you have mu as a function of theta, and theta could be the weights of a neural network. So this could be the weights of a neural network. And then mu theta would map the state space to probability distribution over the action space. So your input is going to be the state input to the neural network. The output is going to be the probability vector over the action space. And now the theta becomes the weights of the neural network, and now you're trying to optimize the weights of the neural network. Okay. So then what we are going to do is replace this mu prime by the derivative of mu with respect to theta, because remember, mu prime is supposed to be the descent direction. So in the case of neural network, the descent direction would be the derivative with respect to theta. Okay, so let's go to this paper. The paper was by Kai-Shing Zhang. This is 2020 SciCon, Science Journal of Control and Optimization. There are multiple authors of the paper. But the cool thing is, Kai-Shing is my academic brother. So he had the same advisor as me during my PhD. So I'm very excited to be presenting the paper of my academic brother. Okay. He's now a faculty at Maryland, University of Maryland. So his algorithm is called random horizon policy gradient algorithm. Okay. What is his idea? So a few things that I want to write. So I'm going to make some changes to this expression. So I'm going to assume mu is a function of theta. J of theta equals to V mu theta. And I want gradient of theta of J theta. And I'm going to replace this mu prime with d mu theta over d theta. Okay, so mu prime changes with the derivative of mu theta. Everything else remains the same. The derivation is there in this particular paper. So if you don't understand how did I get this, you can go back and read this particular paper. Okay. So What else? I think there is one more thing I need to do. Okay, let me erase this one, and I'm going to make a small change. I'm going to divide this whole expression by mu theta and multiply it by mu theta. So let me write it as summation rho I, summation I prime u prime, summation t greater than equal to 0, alpha raised to t, p mu it equals to I prime, p mu theta, given I0 equals to I, mu theta, u prime given I prime, 1 over mu theta, u prime given I prime, d mu theta over d theta, u prime given I prime, a mu I prime, u prime. So I have multiplied and divided by the same number. So I'm not changing anything significantly. And then I recognize that this term is log of gradient with respect to theta of log of mu theta u prime given I prime. This is natural log base e, okay, of mu theta. Any questions so far? I want to pause here for a bit. I want you to look at these equations and let me know if you have any questions.
So the transition curve
Yes.
should be p mu or p mu theta.
Where did I write p mu theta? Because now my mu theta is parameterized. I'm using a neural network to parameterize my policy space. So wherever you have mu, everything changes to mu theta. Wherever you have mu, you changes it to mu theta. Does that make sense? No?
So the mu prime should be changed to mu theta, not mu.
No, mu prime is the descent direction.
Yeah.
Yeah. So the descent direction would be, so what you do is, what you do is you take L mu prime minus L mu divided by mu prime minus mu. And after doing all that, what you would get is d mu theta over d theta here. Okay. So mu prime, just think of mu prime. So this expression is the same as L mu theta plus delta theta minus L mu theta over delta theta. Okay, and L mu theta, this is equal to 0. And this one, as delta theta goes to 0, becomes d mu theta over d theta. So that's roughly what the derivation looks like. Any other question? Okay. So this is what I want to estimate. So I want to come up with. So this is the true gradient. Okay. So my goal is to come up with a sample-based algorithm that can compute this, and I can get the gradient, the unbiased gradient estimate for this particular thing. So the goal is use samples to estimate gradient theta of j theta, but I want it to be an unbiased estimate. Okay, and so there are two things that I need to estimate in order to be able to estimate this gradient of j theta. One is to be able to sample from this particular distribution. So I need to be able to sample I prime and mu prime from this distribution. And then this derivative is easy to compute because you have a neural network. I'm sure all of you know how to compute the derivative of a neural network. You've done it in a bunch of assignments by now. But I also need to estimate this advantage function of mu theta. So I have to estimate two things. Generate I prime u prime from the correct distribution, and then estimate a mu theta I prime u prime in order to be able to compute this gradient. All of you agree that those are the two things we need to do? Okay. So let's look at the estimation of a mu theta. So a mu theta is q mu theta minus v mu theta. So I need to estimate the q mu theta, and then I need to estimate the v mu theta. Okay, so this is where the algorithm kicks in. So estimate q mu theta of IU. So how do I estimate this? So I'm going to initialize I0 equals to I, U0 equals to U. I'm going to pick T, which is geometric 1 minus square root of alpha, which is the same as square root of alpha raised to T 1 minus square root of alpha. Then use for t equals 0 to capital T minus 1, you have q hat of IU, plus square root of alpha raised to T, the reward R of IT UT. Let me go all the way to capital T time step, and then I'm going to return q hat IU. And this estimate of v mu theta is also going to be the same. It's just that the only step I'm going to change is v hat of I plus square root of alpha raised to T R of ITUT, and then return v hat. Okay. Remember, I have t going from 0 to infinity, and I cannot simulate for infinite number of time steps, but I still want an unbiased estimate of the gradient. Okay. So how do I get an unbiased estimate of the gradient if I'm not letting t go all the way to infinity? What's the idea? Well, the idea is you pick a random horizon, capital T. You see this word random horizon? So what is random horizon here? I pick a random horizon which is connected to the discount factor. So the probability that the random horizon is equal to t is given by square root of alpha raised to t. So this is the discount factor. You take the square root raised to t, 1 minus square root of alpha. So you pick a random horizon, you simulate the MDP for random horizon, random number of time steps, you collect IT, UT, and the reward function, reward signal. You do the simulation for capital T time step. You get an estimate of Q hat IU. So I did not mention, but Q hat is initialized to be 0. So Q hat IU is equal to 0. So you start with IU. You simulate the trajectory for a random horizon number of time steps, random number of time steps. You get the value of Q hat IU towards the end of the random horizon process. That's your Q hat of IU, and you return that estimate as the estimate for Q mu theta. All of this generation, all of this IT, UT, IT plus 1, all of that is generated under the policy mu theta. You do the same thing for the value function as well. You initialize the value function to 0. You pick a t which is geometric 1 minus square root of alpha distributed. You do the same update here, except that now you are computing v hat, so it's no longer a function of u, it's just a function of I, and then you return v hat. So remember that in IU, so the first time step, you always pick u. In the subsequent time step, you are picking distributions according to mu theta, and the same thing is something you're doing here, and then you return v hat. So this gives you an unbiased estimate of v theta, v mu theta. This gives you an unbiased estimate of q mu theta. You subtract the two unbiased estimates, you get an unbiased estimate of a mu theta. Okay, and I'll tell you in some time why exactly this algorithm produces an unbiased estimate. Okay, it's a very cool proof, and I think it's instructive for you to know what the proof is. Now, what about this generation process? So this, remember, this a mu theta is evaluated at I prime u prime. This derivative is evaluated at I prime mu u prime. Okay, so this derivative multiplied by a mu theta, all of this is being computed at I prime mu prime. Now, all I need to do is generate I prime and u prime, which satisfies this particular condition. And for that, he has the following estimator. I'm going to erase the value function thing because that's easy. So I'm going to generate geometric 1 minus alpha a naught phi theta k, sorry, u naught I0 and the gradient estimator. Let me use GT. Well, so I compute IT I0, U0, R0, I1, U1, R1. I collect this all the way up to ITK, TK plus 1, TK plus 1, R, TK plus 1. So this is again random horizon. So I'm coming up with a horizon length using a geometric distribution. I'm simulating a trajectory, and then I look at this particular value, ITK plus 1, UTK plus 1. This distribution is the same as this particular distribution that I was looking for, which is IT equals to I prime, mu t equals to U prime. So this is basically distributed. This has the same distribution. This number has the same distribution as I prime and U prime. So once you get this particular value, you call this estimator in order to compute Q mu theta of ITK plus 1, UTK plus 1. And then you compute the gradient. You substitute all of the terms here in order to compute the unbiased estimate of this particular gradient. Is the algorithm clear? So then compute gradient theta of log mu theta of u tk plus 1 given I tk plus 1 a mu theta I tk plus 1 u tk plus 1. So it's a complicated expression, but you generate this, which has, so you have a different horizon distribution here that allows you to generate I prime, U prime, and that you can evaluate the gradient by computing this particular value, and that gives you an unbiased estimate of gradient of theta, j theta. And now you can start from multiple initial conditions. You can pick multiple I0, combine all of these gradients. You can compute these gradients on different simulators, combine all of those gradients together, add it up, you get another unbiased estimate of gradient of theta, j theta. So this algorithm is here. This algorithm is here. Yes, please.
So you have a policy distribution parameterized by theta, and then you extend that trajectory?
Right.
Okay.
Yeah. You're using that mu theta. Oh, I'm sorry. This is not pi theta k. This is mu theta k. So you pick. So you already have the current policy theta k or mu theta k. You use that to generate the trajectory. You compute this gradient. You run one step of the gradient descent. So theta k plus 1 equals to theta k minus or plus, sorry. Because I'm doing gradient ascent, I want to maximize this function, gradient of theta, j theta. So instead of this gradient, you cannot compute this exactly, but you can compute the unbiased estimate, and then you substitute the unbiased estimate here. That's the idea. Okay. So all in all, if you look at papers before 2020, you will find some gradient estimation method for evaluating this expression, but those are all biased estimators. Okay. Because those are biased estimators, sometimes it converges, sometimes it doesn't converge, sometimes you have a long time to convergence, sometimes there are lots of errors, sometimes the variance is too high. So whatever. So what people used to do is they would cherry pick the results, and they would show only those results, that their algorithm is best because their algorithm works best because whatever, ABC. right? But the point was they were all using biased estimators of the gradient. So this was always the biased estimate. So if you look at their simulation section, everything contains the biased estimate. This paper was the first one to prove that they have an unbiased estimator for gradient of theta j theta, and therefore it can be used reliably for solving this problem. And under certain conditions, you can show that this algorithm converges almost surely to the locally optimal solution. And that convergence is because of stochastic approximation theorem, something that we have covered in the past, right? So in stochastic approximation theorem, one of the requirement was that you have an unbiased estimate for the stochastic approximation to work. So they were able to make stochastic approximation to work to converge to a locally optimal policy because they had an unbiased estimate here. This paper doesn't have a lot of citations, maybe like 150 or so. So which means that this algorithm has not yet percolated in the literature. Hopefully somebody will pick up the paper at some point of time and start using unbiased estimate for the policy gradient method. So the only thing I want to show you is why should this algorithm produce an unbiased estimate of Q hat. So let me give you that particular proof. But before that, I want to make sure that you all understand the implication of this particular result. Any question?
So I have a question.
Yes, please.
So when in this random horizon algorithm, okay.
Yeah.
So when the author is updating the Q and the V,
Yes.
is he assuming finite state or action, or is
Everything is finite state, finite action. Okay. So I have not, in the class so far, I have not talked about continuous state, continuous action, but I'm still mentioning because we are moving in that particular direction. Okay. So all of this is for finite state, finite action.
So for finite state space, finite state and action space, these updates will be unbiased.
Will be unbiased.
But with function approximator, the function approximator may introduce bias.
May introduce biasness.
But it's due to the function approximator.
That's right.
Okay.
That's right. Not because of the estimator itself.
Okay.
So if you think about the earlier papers, they were biased both because of the function approximation class and because of the way they were estimating the Q function and the value function and so on and so forth. Okay, so this one corrected at least for that part. The function approximation is not in your hands. Okay, so we'll get to it in a bit, but in maybe like next week or the week after that. But yeah, you could have biasness because of function approximation as well. Any other question? Okay. Okay, so expected value of Q mu theta of IU is summation, expected value of summation t equals to 0 to, let me use t prime here, t prime, yeah, t prime, because I want to distinguish this t prime, this random horizon with this random horizon. The two random horizons are different. So t prime of alpha raised to t over 2 r of it ut. So remember that IU is the beginning, IU is the initial state. So I naught equals to I, U naught equals to U. I'm simulating this trajectory under the policy pi theta. So let me write, sorry, mu theta. So let me write it here. This expectation is this sequence of state and action pairs are being generated according to mu theta. I'm going to write it as the following. This is a neat trick. Indicator function t prime is greater than equal to t alpha raised to t over 2 r of it ut. Okay, so when t is less than t prime, this is equal to 1. When t is greater than t prime, when the small t is greater than t prime, this is equal to 0. This is the indicator function. All of you know indicator function. How many of you have not seen indicator functions before? Okay, so what is indicator function? Indicator over a set. This is 1 if x is in A, or if, well, in this case, if it is true. So if A is true, and 0 if A is false. So A is certain condition here or certain set, and indicator function of A is equal to 1 if A is true, and it's false if it's equal to 0 if A is false. So that's what indicator function means. So when this small t is less than t prime, this takes the value 1. When small t is greater than t prime, this takes the value 0. So I get exactly the same expression that I have here. This t prime is generated independently of this it and ut stuff. So I can write it as expectation of summation t equals 0 to infinity, expectation of the indicator function of t prime greater than equal to t times alpha raised to t over 2 it ut. Right, I'm doing the iterated expectation. So I have expectation with respect to t prime and expectation with respect to these random variables. But this one is independent of these random variables. So I'll take the expectation with respect to this first, and then I'll take expectation, the outer expectation, with respect to these variables. This term here is equal to the probability that t prime is greater than equal to t. Okay. This is probability of t prime equals to t. So how do I compute probability of t prime greater than equal to t? I just have to sum it up from t to infinity. So let's do that. This is summation L greater than equal to t square root of alpha raised to L 1 minus square root of alpha. What is this equal to? So 1 minus square root of alpha is a common term, so I can take it out. And what is this summation of square root of alpha raised to L? L goes from t to infinity. Anybody? Square root of alpha raised to t over 1 minus square root of alpha. Right? So this expectation is equal to alpha raised to t over 2. So this is the same as expected value of t goes from 0 to infinity alpha raised to t r of it ut. So I have alpha raised to t over 2 here, alpha raised to t over 2 here. Both of them multiply, we get alpha raised to t, and then I have the usual reward function. Right, so very simple idea to get an unbiased estimate of the Q function, but for whatever reason, this was discovered back in 2020. Okay, you can apply the same trick here for this particular, for tk plus 1, and you can show, and it's there in the paper, you can show that the gradient of theta j theta, if you take the expectation of this particular term, if you look at the expectation, this is the same as gradient of theta of j theta. To take the expectation of this term, it's the same as gradient of theta j theta. So this gives you an unbiased estimate of j theta, gradient of j theta. Okay, any questions so far? No questions? Okay. So what have we done so far? We have said that, look, if we have the model, I can compute the policy gradient exactly. And then there are a whole bunch of algorithms to use the policy gradient in order to solve the problem. We have policy gradient, vanilla policy gradient, we have TRPO, we have PPO, and then we have soft actor critic. Then we said, look, policy gradient, we want to be able to use samples to be able to compute the gradient. Now, whenever you are doing gradient descent, you ideally want an unbiased estimate of the gradient. You don't want a biased estimate of the gradient. However, prior to 2020, everybody was using biased estimate of the gradient in order to do policy gradient. And there were numerical issues. Okay, you needed to do you need to get a lot of things right. You need to get hyperparameters right. You need to get the horizon length right. You need to do multiple trials and errors for different hyperparameters to figure out when the policy gradient method is working. When it works beautifully. You converge to something that's reasonable and good. If it doesn't work catastrophically. So then Kai-Shing came and said that, look, we need to come up with an unbiased gradient estimate. In order to do unbiased gradient estimate, we need to think from first principles. And we need to figure out what is the horizon length t prime we need to pick in order to get an unbiased estimate of the Q function. And then we need to know for how long we need to simulate in order to get the unbiased estimate of the gradient. Okay, those were the two questions that he wanted to understand. So the first thing he suggested, in order to get unbiased estimate of Q mu, you need to get a geometric 1 minus square root of alpha horizon length. That's the random horizon. And then you get an estimate of Q hat. Then you need to get geometric 1 minus alpha. Remember, there is no square root here. This is 1 minus alpha. So you get geometric 1 minus alpha length horizon length, random horizon. And then you simulate the MDP in order to get the state and action pair at the end of the horizon that's distributed according to I prime mu prime. You compute the gradient at that particular I prime and mu prime. You get an unbiased estimate of the gradient. Okay, so far so good. Now comes another problem, which is I have historical data. I'm treating patients. I've treated patients according to the previous medical protocol. Now I want to figure out what's the most optimal protocol to treat the patient. So now I have past data. I cannot go back and change the data. So all of this, remember, all of this requires you to be able to simulate the system so that you can apply the policy mu of theta. So you need to be, so in order to, for all of these algorithms to work, you need to be able to simulate the system under the new policy, or you need to have access to a page, a web page, where you could change the policy and you could collect the data of what the state action reward looks like. So either you work at Netflix, and Netflix has very high experimentation volume. So they were running like hundreds or thousands of experiments on a single month, right? So either you were able to experiment so much so you can change the policy at your whim and you can collect the data. But in the case of medical protocol, that's not possible. In the case of self-driving cars, so if you look at it from Tesla's perspective, what is Tesla doing? So I don't know if you know, but if you're driving a Tesla, all your data, driving data, is getting collected about there is a pedestrian here, there is a car here, this is the road, this is the lane marking, and so on. All of data is getting collected, and then it goes to Tesla's server in order to figure out what the self-driving algorithm should look like. Now, the policy for driving the car is your policy for driving the car, and there are millions such people on the in the US who are driving their Tesla cars on the road, and all of that data is getting collected. So you have like 1 million different policies, mu theta. You don't have control over it. You can't change that policy. I'm going to drive the way I want to drive. You are going to drive the way you want to drive. I cannot really change the policy. And under that policy, the data is getting logged. And based on that data, I need to now figure out what's the optimal way for driving the car. What's the safe way to drive the car? Okay, that's my problem. Waymo is, how many of you know about this company, Waymo? So Waymo is another self-driving company, just like, well, different from Tesla. So Tesla said, I'm going to let everyone drive the car and I'm going to collect their data. Waymo said, I'm going to drive the car. Like, they hired 10 drivers. They put all the sensors on a car, and those drivers have been driving on San Francisco road since 2007 or 2008, something like that. And they are collecting data in that particular fashion. Even in their case, you have 10 drivers. Your policy is 10 different policies that you are collecting data under, right? So there are situations, either because of legal reasons or because of the way the entire experiment is set up, you don't have the influence over the policy, and you cannot change the policy, and you don't have a simulator to simulate the policy, the new policy, whatever the policy you want to simulate. So all of this method breaks down, because all of this method requires you to use the policy mu theta to simulate all these trajectories and get these rewards. Okay? Yeah.
Is there a problem with Tesla's method because like the policy that's being applied is with my eyes and my spatial reasoning, and then they're trying to figure out what my policy was based on whatever cameras they put on the car?
This is beyond my pay grade question. You have to go ask Elon Musk. See, I think that as long as you are a reasonable driver, as long as you're not driving, as long as all those 1 million people are not driving under influence, I think it's a reasonable policy to use for training the RL problem. Okay. But if, for instance, so in 1 million, if there is one driver who is under influence of alcohol and is driving the vehicle, it's a noise in the system. If it's 1,000 people, it's a very strong noise in the system. And if it is 100,000 people who are driving under influence, and Tesla is collecting that data, it's really a poison data. And now you are trying to do optimization with poison data, and there is a whole bunch of problems if you're doing that. But I'm assuming that 100,000 people are not driving Tesla under influence. That's my assumption, and I think it's a reasonable assumption to make. Okay. All right. So what would you do? So you are in a situation where you have a lot of log data. You cannot do experiments. You cannot do simulation. You are neither in Netflix, nor are you in Google, Google search, or Facebook landing page team. So you cannot really do any experiments. Okay, you are in a medical setting, or you are in Tesla, or you are in Waymo. And now I'm asking you to come up with the best policy, best driving policy, or best treatment policy for a specific cancer. And the question is, how would you solve that problem when the data itself is something you cannot experiment over? Okay, so that's the problem. Think about it for 2 minutes while I erase the board, and I want to make sure I'm cognizant of time. I have 10 minutes. Okay. Awesome. So what would you do in that case? So first of all, think about, where was this problem studied? What are other problems that are similar to this? You want to evaluate a gradient. You want to evaluate a gradient, or rather you want to evaluate an expected value of some function. So in this case, it's the gradient function. So you want to compute the expected value of the gradient of a function under a different transition kernel. Okay, that's the problem. Okay, so I want to take you back to 1950s. 1950s was a golden decade for, what was it golden decade for? Space exploration and high energy physics. Okay, so what is the problem in high energy physics? I have a particle, a muon, whatever that particle is. I don't know much about high energy physics. So you have a particle that got generated due to some nuclear reaction. That particle has a transition kernel, and at some point of time that particle is going to die. Okay, that particle will convert to some other particle. Okay, and that kind of happens in high energy physics. The problem is, if you want to simulate how much time the particle is going to remain in the original particle mode, and at what point of time it will convert to some other particle, so there will be a death of the original particle. You have a transition kernel. Someone like Einstein came up with that. Einstein himself did not come up with the transition kernel, but somebody in the physics community came up with the transition kernel. And now you need to be able to simulate that transition kernel and figure out how long this particle is going to remain alive, after which it's going to die. So that was the problem in nuclear physics, hot problem in nuclear physics, and they came up with a technique called importance sampling. And the idea is, in reality, there is some transition kernel for the particle, which we know from physics. But in simulation, do we have complicated computers in 1950s? Not really, right? So you need to be able to simulate how that particle is going to survive over time using primitive computers. So you need to come up with some method of simulating that to be able to estimate that particular function. So here is the idea. So I'm going to use some other notation right now, because I'll get back to the state action notation later on. So I have a transition kernel P of x prime given x. I have a function f of x0, x1, all the way to x capital T. I want to compute the expected value, goal, compute expected value of f of x0 to xt. For the time being, assume that these are all finite states. Okay, you can do it for continuous states too, but just assume that it's all finite state setting. So this is summation over x0 to xt, f of x0 to xt, p of xt given xt minus 1, p of xt minus 1 given xt minus 2, p of x1 given x0. Right, this is what I want to compute. But this is difficult to compute in simulation. So here is what I'm going to do. I'm going to write it as summation x0 to t, f of x0 to t, p of xt plus 1 given xt over q of xt plus 1 given xt. Oh, I'm using q, but q is already taken. I need another. Okay, k is not taken. Have we used capital K so far? No, right? Okay, so k is the new transition kernel. I'm doing product. T goes from 0 to t minus 1. Maybe I need to put mu of x0. No, rho of x0. So I'll have rho of x0 over mu of x0. So rho is the initial state, the initial distribution over x naught, then this is the transition kernel. This is the function you want to evaluate. This is what we want to, the sum is what I want to evaluate. And then I need to multiply it by mu x naught and product equals to 0 to t minus 1 k of xt plus 1 given xt. So all I have done is divided by something and then multiplied by something, assuming that this something is all positive. Okay. So whenever a transition is feasible, I want k to be feasible. If a transition is not feasible, I want k to be not feasible at that transition. If an initial state is feasible, I want nu of x naught also to be feasible. So all of this is well and good. This particular thing, I'm going to call it L capital T. So I know this transition kernel, it comes from physics. I know this transition kernel because I have constructed it in my head, and therefore I can compute the ratio of these two values. And I can compute the ratio of these two values. I'm going to call it LT. And then this particular sum becomes summation of F LT and then nu and then product of K. So what you have to do is simulate the entire Markov chain according to this particular distribution, multiply this whole thing by LT, which is a scalar value. It's a value that you can compute using your computer. This function f is something that we already know. So I can actually compute this expectation not using this particular simulation, but instead using this particular simulation, and then add this correction, multiply this correction term to f in order to compute the expected value. So this idea is known as importance sampling. And so in the next class, we are out of time. So in the next class, I'm going to talk about importance sampling and how does that apply to off-policy evaluation for this type of problem. And I'll also tell you why it is a bad strategy, but this is the best you can do. It is bad because the variance of this estimator grows exponentially with t. So the variance is pretty bad, as a result of which importance sampling based methods are very unstable. But when it works beautifully. When it doesn't work, it fails spectacularly. So we'll talk about all those considerations in the next class. Thank you.